You know, every single piece of tech you love, your phone, your laptop, your TV, it all has this tiny little sliver of silicon right at its core. But here's the wild part. Pure silicon is, well, kinda useless for electronics. So today, we're gonna pull back the curtain on the incredible trick that turned this basic element into the absolute bedrock of our modern world. Let's dive in. It all boils down to this one massive question, right? How in the world do you control electricity on a scale so small you can't even see it? How do you create those billions of on and off states that make up all the data in our lives? The answer, as you might have guessed, is all about taming silicon. So our story starts with something called an intrinsic semiconductor. Just think of it as silicon in its most perfect, most pristine form. We're talking about a flawless, ultra-pure crystal, not a single impurity to be found. Now, in this perfect little world, every single silicon atom is locked in tight, bonded to four of its neighbors. They're all sharing electrons, creating this super strong, super stable structure. There are no loose ends, no spare parts. It's just a perfectly ordered, perfectly balanced grid. But, and this is a huge but, that perfection is actually its biggest weakness when it comes to electronics. So, what's the problem with being perfect? Well, think about it. For electricity to flow, you need charges that can move around. But if every electron is locked perfectly into a bond, electricity has literally nowhere to go. It's stuck. Okay, I should say it's not a total insulator. Just the normal heat in a room provides enough energy to kind of jiggle the crystal and knock a few electrons loose from their bonds. And when an electron pops out, it leaves behind an empty spot. We call that a hole. So now you have a free electron that can move around, but the number of these is, well, it's ridiculously small. And when I say small, I mean, get a load of this. For every 10 trillion silicon atoms, you get just one free electron. One. That's it. You are absolutely not going to build a supercomputer with that. The bottom line is, pure silicon is an awful conductor of electricity. Just terrible. This analogy really paints the picture, doesn't it? A great conductor, like copper, is like a massive 12-lane superhighway just jammed with cars, the electrons, all ready to go. Pure silicon, it's like a deserted country road in the middle of nowhere, with maybe one car driving by it every couple of days. You just can't run a city on that kind of traffic, and you for sure can't run a microchip. So how do we turn that deserted road into a bustling superhighway? Well, this is where the genius comes in. The answer is a brilliant process that, and I'm not exaggerating, is one of the most important inventions in human history. The solution is called doping. Doping is the secret sauce. It's the magic trick. It's all about deliberately messing up that perfect silicon crystal, but in a very, very precise and controlled way. We intentionally introduce tiny amounts of other elements, impurities, with one goal in mind: to massively boost the number of available charge carriers and crank its conductivity way, way up. The whole process is actually pretty straightforward in theory. You take your super pure silicon, you sprinkle in just a pinch of these impurity atoms. We're talking like one impurity for every 100,000 silicon atoms. And that tiny, tiny change completely revolutionizes the material's electrical properties. It's incredible. But here's where it gets even cooler. Doping isn't a one-size-fits-all thing. By choosing different kinds of impurities, we can actually create two totally distinct flavors of silicon, each with its own unique powers. We call them N-type and P-type. So check this out. To make N-type silicon, the N stands for negative, we add an element like phosphorus, which has 5 electrons in its outer shell. To make P-type, P for positive, we use something like aluminum, which only has 3. That single extra electron or that single missing electron changes everything. It determines whether negative electrons or these positive holes become the primary way electricity moves. All right, let's break down N-type. Picture this: a phosphorus atom comes in and takes the place of a silicon atom in the crystal. Now, silicon needs 4 electrons to make its bonds. Phosphorus has 5, so it makes its 4 bonds with its neighbors, no problem. But it's got 1 electron left over. This 5th electron has nothing to do, so it's just free to wander around the crystal ready to carry a current. Because phosphorus donates this free electron to the system, we call it a donor impurity. And P-type? It's basically the mirror image. This time, an aluminum atom replaces a silicon atom. But aluminum only has 3 outer electrons. It desperately wants 4 to make all its bonds, so one of its bonds is left incomplete. That empty spot is our hole. Now, this hole acts like a positive charge. An electron from a neighbor can easily just hop into the hole to fill it, but that just creates a new hole where the electron came from. So the effect is that the hole seems to move through the crystal, acting like a positive current carrier. Since aluminum is ready to accept an electron, we call it an acceptor impurity. Okay, so this brings us to a super important question, and honestly, it's a really common point of confusion. We've just added stuff that creates free negative electrons or mobile positive holes. So does that mean the silicon itself becomes electrically charged, either negative or positive? And the answer, which might actually blow your mind a little, is a hard no. Not at all. Even after we've doped it, whether it's N-type or P-type, the silicon crystal as a whole stays perfectly, completely electrically neutral. So why? What's going on? Well, the key thing to remember is that we're not just injecting a rogue electron or a naked hole. We are swapping one whole neutral atom, silicon, for another whole neutral atom, like phosphorus. That phosphorus atom comes as a package deal. It has a nucleus with protons, and the positive charge of those protons perfectly balances out the negative charge of all its electrons, including that extra fifth one. The net charge is always zero. We created things that can move, but we didn't change the overall balance of the material itself. So let's just step back for a second. We've taken this nearly useless, barely conductive material, and with this incredibly elegant process of doping, we've created two brand new materials that are just teeming with charge carriers. This one idea, this one breakthrough, is what unlocked the entire digital world. And the scale of this transformation is it's staggering. This chart says it all. You start with pure silicon down here with basically zero conductivity. Then you dope it, and boom, whether it's N-type or P-type, the conductivity just skyrockets. We're talking an increase of thousands, sometimes millions of times. It's a colossal leap. And that right there is the whole game. Doping doesn't just make silicon a conductor, it gives us control. By choosing the impurity and exactly how much we add, we can dial in the electrical properties of silicon with incredible precision. This ability to control conductivity is the fundamental principle behind every single transistor, chip, and electronic device that exists today. So we figured out how to create these two amazing materials, one full of free electrons, the other full of mobile holes. We can make them as conductive as we want, but the real magic, the secret that lets us build diodes and transistors and the processors in our computers, that all starts with the next obvious question. What happens when you take a piece of N-type silicon and stick it right up against a piece of P-type? Because that's where things get really interesting.